Okay.
Okay, so please record it. Okay. Okay, so this, like I mentioned earlier, today is one of the most important lectures of the whole semester. And so we are talking about the topic so-called eigenvalue, eigenvectors, and also this very unique decomposition called singular value decomposition, or SVD. Okay, so let's start. So what are the, when we have a vector so-called when we have a matrix called A, okay, so let's say that it is a square matrix with the n number of rows and n number of columns. Okay, we can find what is called the eigenvalues and also eigenvectors of this matrix always. Okay, and there will be like many pairs of these eigenvalue eigenvectors. Okay, maybe some of you have seen it before, and so we, but anyway, but maybe some of you have not uh, seen it, so we'll go through it. Okay, so this lambda is called eigenvectors, eigenvalues. Okay, so they are scalars, and this is the eigenvectors. Okay, so the concept of having eigenvalues and eigenvectors out of the matrix A, any arbitrary matrix A, uh, because the why we do this, because this concept of eigenvalues and eigenvector, they will give um, more information of a matrix. Okay, if this matrix happen to be the matrix that describe the system, for example, or describe the linear system, it will give you some sort of ideas about some like what some type of stability. Okay, this is in terms of system. It gives you idea of convergence. Okay, in many algorithms, if you can express the system as a matrix system, a lot of time you can tell whether it has some stability issues or it has some convergence issues, by just looking at the matrix A. But more importantly, it will help you on the unique decomposition for matrix A. Okay. So if you remember, during this lecture, during this class, we have already tried to decompose matrix A by using various approach, right? For example, A is equal to L times U, A is equal to LDW, or even like the Koleski decomposition. Okay, so this one, it will lead you to another unique decomposition, so-called SVD, or singular value decomposition. Okay. Okay. So let's look at the definition. If we have a given a square matrix A, okay, which can be either real numbers or it can be complex numbers, okay, then an eigenvalues, it can be a real or a complex number eigenvalue. Okay, lambda is said to be eigenvalue. If it satisfied this equation, okay, it is said to be eigenvalue when if you multiply ax, it is equal to lambda x. Okay. And so this is called eigenvalues. I think we wrote it up there already. And this is called eigenvectors. Okay. So in a way, and we also need to note that the vector x cannot be equals to 0. Okay. So if you see this type of equation, ax is equal to lambda x, what does it mean? It means that if you have a matrix of a system and you multiply with this vector x, then it leads to the change of length of the vector x. Okay. So let's take a and let's try to decompose it and then see what we get. Okay. So from the previous page, we have ax is equal to lambda x. Okay. I don't put an underline at lambda because it's a scalar value. Okay. So let's try to see how we can find the all the eigenvalues and also all the eigenvectors. Okay. So there are different approaches, but what I can do is I can just move the right hand side to the left hand side like this. Okay. Okay. Then I can pull out the vector x. Okay. You notice that x is at the back. So when we pull it out from the equation on the left, from the expression on the left, we have to pull it to the back. Okay. So what will we get, Panatson? Can you tell me if I pull x out of at the back, what do I get at the front?
Matrix A
The matrix A minus
has lambda multiplied with
lambda,
identity matrix.
yeah, and then identity matrix, of course. Okay. So this is it. So we say that the vector x is not equal to 0, right? Okay. So from here, how do we solve it? We can take a determinant on both sides. Okay. If you don't remember what determinants is, then we'll solve it a bit later. So we take determinants on both sides, and we can use the property that determinants of matrix, let me see, B times C, it is equals to determinants of B times determinant of C. Okay. So I'll try to put the underline always when I write it out so that we know the difference between the scalar and also from the vectors or matrices. Okay. Another expression, instead of writing determinant like this, we can write it like this, with sort of like absolute value. Okay. But when we do this with the matrix, we know that it is the determinants. Okay. So you can write it either ways. Okay. So if I take the determinant on both sides of the equation, okay, of the star, what do I get? So I'll get, oops. So I'll get the determinant of the first term, which is a minus lambda I, multiply with the determinant of x, which is equal to 0. Okay. If the determinant of x is not 0, we will have that the determinant of a minus lambda I will be 0. Okay. So that's one assumption. Okay. That the determinant of a is not 0. Okay. So this is the condition of how we do it. So let me put in red color so that you see very clearly. Okay. So we'll use this property to find lambda. Okay. So let's look at some example, and then after that, then we will try to compute the eigenvectors altogether. Okay. So let's look at an example. Okay. Okay. Example number 1. So okay. Let the matrix A to be equals to let's say is 1 0 0 0 1 0 0 0 0. Okay. So let's find all lambdas and eigenvectors. Okay. So we will use the property from the previous page, which is from the property that the determinant of A minus lambda I is equals to 0. Okay. So what do we get? So we will get the determinant of 1 0 0 0 1 0 0 0 0. Okay. And then minus lambda I. What do I get? Thananpat, what do I get for this part? This thing is 1 0 0 0 1 0 0 0 1. If I multiply with lambda, what do I get? G, are you there?
Lambda is 1 0 0.
I multiply with lambda.
Lambda lambda 0 0.
Okay, so I get lambda 0 0.
0 lambda 0.
Okay, and then last line.
Lambda.
Yes. Okay. So that's that, and then so we can find determinant of these. So we can just do element by element subtraction, right? So we get 1 minus lambda, 0 0 0 1 minus lambda, 0 0 0, and then minus lambda. Okay. And this will be equals to, oh, sorry, this is not a matrix. It has to be just numbers. The value of determinant is just a scalar number. Okay. What did I think of? Okay. This will be 0. Okay. And how do we find the determinant of a matrix 3 by 3? Okay, let me go to the next page to write the property on how to find the determinant and then come back to this slide. Okay. So if you are given A is equal to, let's say this is A1, A11, A12, A13, A21, A22, A23, A31, A32, and A33. Okay. So how do we find the determinant of A? It can be found from this. Okay. You can use any rows or any columns. Okay. Okay. You can use any rows or any row or any columns. Column doesn't matter. Okay. So let's say I use row number 1. Okay. What am I gonna get is to find the determinant. If you look at row number 1, okay, let me put a red color so that you see it. Okay. So this is what we will get. So we will get minus 1 to the power of row index plus column index, which is 1 plus 1. Okay. And then multiply with the determinant of the remaining matrix Okay, the remaining matrix that exclude, meaning that you don't count row I and row J. Okay, this is row 1 and no, row I and column J. Okay, meaning that you can just do this. Just take out row number 1 and column number 1, because here we are talking about A11, right? And then here I have to multiply with A11, sorry. Okay, and then in here, this is the determinant of the remaining matrix that excludes row 1 and column 1. So you have A22, A23, and then A2, A32, and A33. Okay. And then next you add it with the second element, which is A12, multiply with -1 to the 1 plus 2. And then the remaining matrix by not considering row 1 and column 2. So you get A21, A23, A A31 and A33. Okay, and you just repeat this, and then the last one is A13 and multiply with -1 to the 1 plus 3. Okay, and then the remaining matrix that doesn't include row number 1 and column number 3. So this is all you have, which is A21 and A22, A31 and A32. Okay, and that's all. Okay, and for a 2 by 2 matrix, let's say is the like this, A, B, C, D. Okay, the determinant of 2 by 2 matrix is like this, can be found from 1 over A times D minus B times C, and multiply with the matrix. Oh, sorry, this is the not the inverse. Sorry, not the inverse. The determinant is equals to A times D minus B times C. Okay? So meaning that you can expand, you can compute each of these, the determinant, 3 of these, and just multiply whatever you have. Okay. So this is like a formula. So you can use this concept to find the determinant for a 4 by 4, 5 by 5, and so on. So you can extend this to matrix with more rows and more columns. Okay. So now let me go back to the previous page and try to compute the determinant. Okay. You notice that this is the determinant of these 3 by 3 vectors, and this is actually quite simple because it is, we can, for example, look at row number 1. Okay, you can look at any row, you can look at any row, any columns, and you use the same approach. Okay, so let me try both way. Let's say I focus on row number 1, okay, and see what is the solution, so that we at the same thing. Let's say this is row number 1. Okay, so what we will have is we will have 3 elements, which is 1 minus lambda, 0 and 0. Okay, so for the first term, I have -1 to the row number 1, column number 1, which is 1 plus 1, multiply with this value. Okay, and multiply with the remaining matrix, because I don't want to count row number 1 and exclude column number 1. All I have is the matrix, which is 1 minus lambda, 0 and 0 minus lambda. Okay, the reason why I say that this is easy, because if I continue with the next element, because it is 0, So when it's multiplied with anything, I get 0. And then the last one is also 0. So I can just say that, I mean, it doesn't help, okay? So here I can say this is 0. And here minus 1 to the 2 is just 1. So I have 1 minus lambda, okay? And then here is the determinant of the 2 by 2. I can use the formula from previous page, which is A, B, C, D. So I get A multiplied with D. I get 1 minus lambda. And multiply with the minus lambda. Okay. And minus B times C, which is 0. So I get this. So I can write it out. Okay, so I'll have 1 minus lambda multiply 1 minus lambda. Minus lambda I don't need, right? I can just say lambda is still 0. Okay. So if you look at this equation, what do we get for lambda? Thanatson. I don't know who's in the class today. So we have Thanatson and G, right? Okay. Only 2 people, right?
No, I'm also here.
Oh, Pio, you're here as well. Okay. So I ask you then, Pio. So if you see this equation, what are the possible values of lambda?
Zeros and 1.
0, 1, 1. Yes.
Yes.
So for a matrix of size 3 by 3 or n by n, we will have n values or 3 values of lambda. Okay. This is like square. So it means we have 2 lambda of 1, 1. Okay. But the unique lambda here just 0 and 1. But we have 3 lambdas. Okay. So we have 3 eigenvalues. Okay. Which are lambda equals to 0, 1, and 1. Okay. Of course, you can try using other rows or other columns to try to find this as well. Okay. Let's say I focus. Okay, let me work on the side just to show you. Let's say that I focus on column 3. Okay, on how to find this solution. So let me remove this first. Okay, so let me try to compute by looking at columns number 3. Okay, so I have 0 and multiply with the remaining matrix is 0, right? And then I have 0 multiply with minus 1 to this row number 1, column number 3, right? And multiply with the remaining remaining matrix, but this is 0, so I don't need to do anything. Then I add it with next one is 0, multiply with minus 1 to the row number 2, column number 3, and multiply with the remaining matrix is also 0, right? And then I add with the last one. Last one is minus lambda. And then I multiply with the determinant of the matrix that doesn't include here. Actually, sorry, I forget to put the matrix cover. Okay. So I will exclude. So this is element number 3 by 3. So I will exclude all the row number 3 and column number 3. What I have is this. So I have 1 minus lambda, 0, 0, 1 minus lambda, right? So this will be equals to lambda minus lambda multiplied with the determinant of 1 minus lambda, 0, and then 0, 1 minus lambda. Okay. Okay, I should put matrix. So this will be minus lambda and then multiply with 1 minus lambda squared which is 1 minus lambda square, and then minus 0. So I don't need to put anything. It has to be equal to 0. Okay. So we get the same solution no matter how you which row or which column that you try to focus. Okay. Okay. Any questions so far? You can also get lambda to be imaginary number like I, something like that as well, depending on what A is. Okay. So next, that's what we have, right? We have the eigenvalues of 0, 1, 1. Okay. Next, let us find the eigenvectors, which is x. Okay. So for each eigenvalue, we will have a specific eigenvectors. So then we will have x1, eigenvector number 1, eigenvector 2, eigenvector 3 related to eigenvalue number 1, eigenvalue number 2, and eigenvalue number 3. Okay. So how do we find it? So actually there are two cases, right? We only have two unique eigenvalues. So first, let's look at the case where lambda 1 is equal to 0. Okay. So what do we find? Well, from this expression that eigen lambda multiplied with lambda 1 is lambda 1 multiplied with x. Okay. Oh, sorry. No, I should look at another thing. Oh, no. That's wrong. Okay. From the expression, from the definition, Ax, where x is eigenvector, if this is eigenvector 1, corresponding to eigenvalue number 1, I should have Ax1 is equal to lambda 1 x1. Okay. So this is from the early definition here. Okay. Because in this case, lambda 1 is 0, so I can say that Ax1 has to be 0. Okay. So in other words, for this case, x1 is a null space of matrix A. Okay. So let's see what is matrix A. So previously we have A is 1, 0, 0, and then here is 0, 1, 0, and 0, 0, 0, right? Okay. So we'll multiply with this vector. So let me call this as x1, y1, z1. Okay. So it has to be equals to, wait, let me see. So this has to be 0 vector, right? Okay. So what is the solution for this x1, which is x1, y1, z1? Okay. You notice that in this problem, do we have any free variables here? This has already been written in a very nice form. So we have these pivots, non-zero pivots, and then we have this 0 pivot, right? Okay. So that means that when you solve this equation, z can be anything, right? So, okay. So here you can say that z1 can be anything. It's a free variable, right? And for y, how about y1 and x1? Tanatson, what is the solution for x1 and y1 in this vector?
x1 go to 1.
No. If you multiply this row number 1 with x1, y1, z1, what do you get? If you multiply
x1 equal to 0.
Yeah, exactly. So if you do this, you get that x1 and y1, they are both equal to 0, right? But then z1 can be can be anything because it's a free variable, right? It's a free variables. So you can say that in this equation, the solution for this eigenvector, it has infinite solution. Okay. So for example, in this case, I can let x1 to be equal, in general, it will be equals to 0, 0, 1 and multiply with z1. Okay, where z1 can be anything. It can be 0, it can be real numbers. Can z1 be complex or imaginary numbers? It can be anything, right? Okay, so for specific case, let me let z1 to be 1. So I get that one possible value for eigenvector corresponding to lambda 1 0 equal to 0 is 0, 0, 1. Okay. So there are many solutions in this case. Okay. So next, let's look at the next case. Previous here we looked at this case, no? Lambda is equal to 0. So next, let's look at the second eigenvalue, which is eigenvalue is equal to 1. Okay. So here we can do the same thing from a x2 equals to lambda 2 times x2. Okay, this is from the definition. And in this case, lambda 2 is equal to 1, so it is equal to x2, right? So how do we find for x2? Well, very simple approach. I can just move x2 to the left-hand side. So I get this, okay? And I can pull x2 to the back. Okay. I cannot pull to the front because for matrix multiplication, there's no property of the commutative property. We cannot switch order. Okay. So I'll have a minus I multiply with x2 has to be 0. Okay. This is a vector. Okay. So how do I do it? So A, in this problem, A is 1, 0, 0, and then 0, 1, 0, and the last row is 0, 0, 0. So we minus the identity matrix like that. Okay. And then we multiply with, I expand it to x2, y2, z2. Okay. Just for solving the solution. So we get all 0 here. Okay. So here we can subtract it. So what do we get, pure, when we subtract these two? How about G? What do we get when we subtract these two? I cannot see
0,
whether you're here.
0, 0,
Yeah, you get 0, 0,
0,
0.
0,
Yes. And
0, 0, and minus 1.
yep, that's it. Okay. And so we'll multiply this with x2, y2, and z2. Okay. We have to get all 0. Okay. So can you think, Tanatson, what do we get for z2?
X1 and X2 are free variable.
Yeah, they're free
And
variables, so they can be anything, right? Okay.
Z2
How
is
about
equal to
how about
0.
z2? What is z2?
0.
Say again.
0.
It has to be 0. Yes. Okay. So in this case, it means that x2 is equals to x2, y2, 0, right? So there are infinite solution. Okay. So we can put one example. Let's say x2 is equals to 1, 1, 0, for example, or it can be 0, 1, 0. It can be anything, right? There's many solutions. And then for x3, because x3 also corresponds to the eigenvalue of 1, so well, in this case, let me use this value, so you get something else as well. I can just say 1, 0, 0, for example. Okay, just an example. Okay, so if you go to Matlab, let me go to the Matlab first. Okay, so let's take a look at this Matlab. So first of all, if you want to find eigenvalues and eigenvectors, you can use the command called EIG. So let's take a look at this command together. So if I try to search what it is for, okay. So this is what it is. Okay. So this command is a function that produces eigenvalues and eigenvectors. Okay. If you don't put any output, you just get the eigenvalues. Okay. But they will put them in terms of the diagonal matrix. If you put output like this, V and D, then you get both the eigenvalues and eigenvectors. Okay. And anyway, so you can compute all these as well. So let's take a look at our question. So what do we have here? So we have A is equal to 1, 0, 0, and 0, 1, 0, and then 0, 0, 0. Okay. So it's A. Do I put it right? Okay, that's it. If I just want to find the eigenvalues, this is what I do. I will just put this command. Okay. So I get 3 eigenvalues, which are 0, 1, 1, right? Okay. Then what if I want to find the eigenvector as well? Then I have to put the command like this. Okay. So this V is the eigenvectors. They put in 3 columns in this case. So they put each eigenvector in each column. And then for the diagonal matrix, for the D is the eigenvalue matrix. Okay. And we put the eigenvalues in at each diagonal element. This is what we get. Okay. So for the diagonal matrix of the eigenvalue, we have 0, 1, 1. And for eigenvectors, this is what we have. Okay. So that's it. So I think in for Matlab, what they try to do is for the eigenvectors, they will give you the solution that each column has the size of 1 or magnitude of 1, and also they try to make V each column as independent as possible. Okay. So that's how so that's how it works. Okay, so now let's see what so let's go to next page and look at how we can decompose this. Okay, but this is not SVD. Okay, it's just decomposition with eigenvector and eigenvalues. Okay, so theorem. Okay, first of all, given that lambda I is not equals to lambda j, we will have that the eigenvalue xi and xj are linearly independent as always. Okay. Okay. Or you can just say that x1 and xi and xj, they are diagonals. Okay. Or if you multiply xi transpose with xj, it will be equal to 0. Okay, so that's the same thing. Okay, so also we can express, once we know the eigenvalues and also the eigenvectors, we can express the matrix A as follow. We can write it like this: A multiply with each eigenvectors as a column vectors, okay, equals to okay. So this comes from the property AX is equal to lambda x, okay? But I just write it out differently, okay? So here is AX is equal to lambda 1. No, A. So here what it is AX1 is equal to x1 times lambda, okay? Or lambda 1 x1, okay? AX2 is equal to lambda 2 x2, and AX3 is equal to lambda 3 x3, okay? So when I write it out like this, I can express, if I express these the eigenvalue vectors as diagonal matrix lambda, and for this matrix of the eigenvectors, if I express as S, okay, so this will also be S, okay. So we can write the equation as AS equals to S, and then diagonal matrix of eigenvalues, okay. So this is number 3, okay. So if you write it like this, I can move S to the right hand side, to the back, and then inverse, okay. Then I will get A is equals to S time eigenvalue vectors multiplied with S inverse, okay. So so this is the one way of decomposition. Let me call this as the star 4, okay. So if S has an inverse, or the eigenvector has an inverse, okay, i.e. that is S inverse exists, okay, we can express A or decompose A like this. So if you remember in the past, we did decomposition A equals to L times U, A is equal to L times dW, right? And then we have for symmetric matrix, we have A is equal to S times S transpose, which is the Cholesky decomposition. Okay. Okay. So this S and this S are different, no? Okay. So what is the usefulness of this type of decomposition? Okay. So I can do this. Usefulness. What is the usefulness of this decomposition? Okay, imagine that I have to compute a square. Okay, which is A multiplied with A. Okay, I can write each A as S times eigenvalue matrix and then S inverse. Okay, and then I can do the same thing and then S inverse. Okay, so what do we get here? Well, we can multiply from left to right, right? Or we can multiply any two of them next together. So if you have S inverse multiply with S, you get an identity, right? So what we get is S multiply with the eigenvalues, eigenvalue matrix, and then S inverse, okay? For the diagonal matrix, if you have something like this, for example, 2 and 3, and you multiply it by itself, this is very simple. What do we get here? Who haven't I called? Pure, what do we get here? Are you here?
Yes.
Okay. If I multiply these two diagonal matrix, what do I get?
So 4.
I get 2 squared, right?
Yeah, yes.
0.
3 square.
Yeah, exactly. Which is, we can write it as 2003 and then squared. Okay. That's how we normally write it. So this is equal to S, which is the eigenvector matrix, and then diagonal matrix square, and then S inverse. Okay. So you can do this, you get something like if you need to find a to the fourth, you just eigenvector remains as it is, and you have the eigenvalue, which is the diagonal matrix to the fourth, and then you have S inverse. Okay. So when you decompose this, if you need to do many operations, it will be very, very easy. Okay. And similarly, if you want to find an A inverse, so what do we get? Okay, I can just write A as S multiply with the eigenvalue matrix and S inverse. If I take inverse, what do I get, Thanatson?
Okay. S inward multiply with eigenvalue vector.
Oh, by the way,
S.
just in case someone forget, if we have like a X times Y and inverse, we will get Y inverse multiply with X inverse. Okay. This is similar to if we have X times Y transpose, we will get Y transpose multiply with X transpose. Okay. It's just a property. Write it down. No? So what do we get here? We get S inverse, right? Is that right?
Yes.
And then we get diagonal matrix inverse, and then we get S inverse. Okay. So what is this thing? Inverse twice. You get S by itself, right? And for the diagonal matrix, what do we get? This is easy. If you have this as the diagonal matrix, to find inverse, it's just 1 over 2, 0, 0, 1 over 3. Okay? So it's very simple, right? To find an inverse as well. And then this is S inverse. Okay. So that's that. Okay. So what are some other important properties? So, well, we can find the determinant and what is called trace determinants. Okay. And trace of a matrix, okay, can be found from lambda. Well, in essence, we can write determinant of A, which is absolute value of A. It can be computed from the products of lambda. Okay, so this is for A n by n. Okay, and if we sum all the lambda together, I is equal to 1 to n. Here, this is what we call here is trace, or this. Okay, trace. Okay, what else should I take a look at? I can give you more example, or maybe we can go further to so then let me take a look at the previous page. So now let us write down what are the decomposition in this case for this problem. Okay, so in this problem we will find that a times x is equals to x times eigenvalue vectors. Okay, or I call s, right, not x. Okay, or a is equals to s times lambda times s inverse. Okay, so from the previous problem, so what we have is, let me see what's the solution previously. Okay. So from the previous example, so we have is equal to 1, 0, 0, 0, 1, 0, 0, 0, 0. Okay. And this is equal to the eigenvectors that we look at. Okay. The first column is 0, 0, 1. And the second column, I decide to use this number just so that they are linearly independent, and multiply with 0, 1, 1. Okay, and multiply with this inverse. Okay, so that's what it means when we do this. Okay, so let me see. What time is it? It's already 5:40. Okay, so let's take a short break for like 5-10 minutes, and when we come back, we will look at the singular value decomposition together. Okay. Or before we look at SVD, maybe we should look at another interesting metrics together. Okay. Okay. Let's come back in 5 to 10 minutes. Okay. Theoravit, Thanatson, can you stop the recording?
Oh, okay.
Okay.